Today we're going to look at section 2.1, quadratic functions and models. So in this section, we'll study graphs of what we call polynomials, and we'll talk about what a polynomial is in a minute. But we've seen some basic functions already. We've seen the linear function. Keep in mind in this linear function, this is what we've seen in the past as mx plus b, where this a in this case is our slope, representing the m, and the b is my y-intercept. We've also seen our constant function and our squaring function. These are all examples of what we call polynomial functions. So the formal definition of a polynomial function, okay, so let our n be a non-negative integer, and a sub n through a sub 0 be real numbers. We don't want a sub n to be equal to 0. Then this function f of x, written in this form, a sub n x sub n plus a sub n minus 1 x sub n minus 1 down to a sub 0 is what we call a polynomial function. Okay, I'm going to take that away for a second. Okay. So let's look at this function. This a sub n we're going to call our leading coefficient. Okay, whereas all of the a terms here are going to be what we call our coefficients. Since a sub n has the highest number exponent here, we're going to call it the leading coefficient. Okay, and now this a sub 0 we're going to call our constant term. Okay. It's our constant term. Notice that it doesn't have an x with it, but it actually does. It has a sub 0 x to the 0. Okay? And what do we know about x to the 0? We know that x to the 0 is just 1. Anything to the 0 power is 1. And so therefore, this is a sub 0 times 1, which is a sub 0. So we call it our constant term. Okay? Now let's talk about the degree of a polynomial. The degree is the highest exponent that I have within my function. Okay? And so this would be called the nth degree polynomial. If I have, say, the linear function ax plus b, the degree is equal to 1. There's an understood 1 when I don't have an exponent there. If I have my constant function c, keep in mind it's really x to the 0. And so it has a degree of 0. Okay? The one we're going to focus on in this section are our quadratic functions. Our quadratic functions are our squaring functions, or x squared. So we're going to look at things that have a degree of 2. So I've mentioned this already, but polynomials, constant functions have a degree of 0, and then our linear functions have a degree of 1, and now we're going to study our quadratic functions. Notice that all of these are what we call quadratic functions. They may not appear to be quadratic, but this first one we clearly see the highest degree is 2. Okay? So it is a quadratic function. Here, if I were to multiply this through, I see that the highest degree of my x squared is going to be an x squared. Okay, so therefore it is also a quadratic function. Here we see it clearly. Here we see it clearly. This one we would have to multiply through. If I multiply through, once again, the highest x value exponent will be a 2, and so therefore these are all have a degree of 2, so they're all quadratic functions. So let's look at the formal definition of a quadratic function. Let a, b, and c be real numbers. We don't want a to be equal to 0, because if it were, then it would take away this first term, and therefore it would only be a linear function, because this would be left. Okay? So, so we call this f of x is equal to a squared plus bx plus c. I read that wrong. Ax squared plus bx plus c is what we call a quadratic function. Okay, so we've seen this quadratic or squaring function before. excuse me, and it has that U shape, which we're going to call a parabola. Okay, and parabolas occur in real life, so this is something that are used daily when we think about, say, the satellite dishes. They have a parabola shape, as well as a spoon has a parabola shape, and then the flashlight. If we were to open a flashlight, the reflectors to help the light to reflect and be bigger so we can see it has a parabola shape. I'm going to look at the pictures. Okay, we have seen that the quadratic functions are even functions. So that means they're symmetric with respect to the y-axis. But if the function is moved, so let's look at this first function here. Okay, it's on the y-axis, so here's our y. Okay. Each parabola has what we call an axis of symmetry, and we're just going to call it an axis, okay, which it is symmetric to. So this line here is our axis, and then this line here is our axis. Okay? The point where this axis or axis of symmetry hits the parabola, this point here and this point here, are what we're going to call the vertex. Notice in this first graph, okay, we're going to say here that our a, which is our a sub n, our leading coefficient, is greater than 0. Okay? So since it's greater than 0, it's positive. If that a is positive or greater than 0, then we notice our graph opens upwards. Likewise, here for this graph, if our a sub n is less than 0, so this is our leading coefficient, is now negative. If it is negative, then our graph will open downward. So to reiterate what we said on our last graph, when a leading coefficient is positive, the graph is open upwards. Okay, so we have a graph that looks like this. So when my a sub n is greater than 0, when my leading coefficient is negative a sub n is less than 0, then my graph opens downwards. So we're going to look at now the simplest type of quadratic function. This simplest type is going to be in the form of f of x is equal to ax squared. So we don't have those second and third terms here listed. Okay? This is a graph who has a parabola. Is a parabola who has a vertex of 0, 0. Okay? When a is greater than 0, okay, then this vertex is the minimum value. So the point minimum y value on the graph. Okay? When a is less than 0, okay, that means our graph is going downward. Then we say that this vertex, this point 0, 0, is the maximum point. So we have the minimum point here and the maximum point. This is where our a sub n is greater than 0, and this is where our a sub n is less than 0. So when sketching the graph of f of x equals a sub x, okay, keep in mind we're going to have our parent function. We're going to remember that graph y is equal to x squared as a reference. So if we recall, y is equal to x squared looks like this. Okay, and then our a greater than 0 or less than 0, we'll see what happens when we graph a few functions. So let's graph these two functions and compare it to the graph x squared. So we've actually done this in our last chapter. Okay, and so let's graph f of x. So if I graph f of x, okay, I'm going to graph my parent function, which is my x squared function. Okay. Now, what does this 1/3, this a sub n? It is positive, so I know my graph will continue to be up. But remember, we have a shrink, so it's like pushing down at these edges. And so my graph is going to be the same graph. So this is f of x, but it's going to be a little wider. Okay. Now let's look at b. Okay. If I look at b, my parent function again is x squared. Okay. Now I'm going to graph the 2. The 2 tells me I'm going to stretch, so I'm going to pull up on these edges. When I pull up on these edges, my graph is going to be skinnier or smaller. So the graph of this function, please excuse that, straighten that up a little bit, is going to look like this. So this is the function g of x. So you see here formally these graphs drawn. We see we have a shrink, or my graph is wider. Okay. And here we have the function, we see the function stretches, so my graph is narrower or skinnier is what I've called it. So as we mentioned in that last example, that we noticed that the A determines how the parabola, how wide or skinny it is. So when A is small, the parabola opens wider. Okay, when A is then when A is larger. Okay. So let's remember our what are these? Shifts and reflections. So if I'm adding f of x plus or minus c, please excuse me, let me go back. Plus or minus c, that tells us if we're going to go left or right on my graph. If it is plus, we go to the left. If it is minus, we go to the right. Okay. When I have the function plus or minus c outside of the parentheses, this tells if I'm going to go up or down. Plus, we go up. Minus, we go down. Okay. If we recall, f of negative x, all right, if we have this, we know, and it equals the function, we're going to have a reflection about the y-axis. Okay. And if the function then equals negative of f of x, then we'll have a reflection about the x-axis. Okay. So these are some rigid transformations. We've seen this in the last chapter. Okay. So let's look at these functions here. Okay. So this first function, what do we notice about this graph? Okay, so we have a negative a in this case, which is less, so a sub n is less than 0. So my function is going to be, we saw a reflection about the x-axis, but it also, we notice, is pointing downward. Okay, the plus 1 says I'm going to shift up 1 unit. Let's look at our second function. When we look at our second function, we have our parent function x squared. Okay? The plus 2 means I'm going to go to the left 2. The minus 3 means I'm going to go down 3. Okay? And so I have a positive, so it is pointing upward. Okay? As well as, let's notice now, for here, my axis is the line x is equal to 0. Okay? Or just the y-axis. But here, my axis is x is equal to negative 2. So what do we notice? That happens to be the x coordinate of the vertex. It is a line, so we must put x is equal to negative 2. Okay? And so now my vertex is negative 2 and negative 3, which is this point here. It is the lowest point or the minimum of my graph. So we've been looking at quadratic equations of the form ax squared plus bx plus c. Now we're going to look at what we call the standard form of a quadratic equation. And it reads as follows. F of x is equal to a times the quantity x minus h to be squared plus k. If I can get my function into this standard form, it will be easy for me to actually sketch this parabola, right? Because it's going to directly identify my vertex. If I can identify what h and k are, then I already have my vertex, okay? And so let's read the standard form of quadratic formal definition. This quadratic function f of x is equal to a times x minus h to be squared plus k. Of course, we want a to not be equal to 0, is in standard form. The graph of x is a parabola whose axis is the vertical line, x is equal to h, okay, and has a vertex of h, comma, k. When a is greater than 0, my parabola opens upwards, and a is less than 0, it opens downwards. So if I have it in this standard form, it will be very useful to draw the graph, okay, without even using our shifts. So what I'm going to do is go back to the last slide and look at it and see if we can identify the vertex and the the vertex and the axis. Okay, let's go back to this f of x and g of x. So keep in mind, this is our standard form. Okay, and so if we look at f of x, we can rewrite this as a negative of x. And since it's just no h here, we'll put plus 0 to be squared plus 1. So if I see that in this form, I know that this negative tells me that my graph is going to be downward. Okay, and then if I look at my h value, x is equal to h implies that x is equal to 0 is my axis. Now, if I want to find my vertex, I just look at the h value and the k value. Keep in mind this is minus h, and so this is plus 0. It doesn't matter. So I have 0 plus k, so we just take this value 1, which verifies here that I have a vertex of 0, 1. Now let's look at g of x. If we look at it, we see it's actually already written in my standard form. So my a here is understood to be 1. Okay? And since 1 is positive, we know my graph is going to be open upwards. Now I can look at my axis. My axis is x is equal to h. Keep in mind, I can rewrite this as g of x is equal to x minus a negative 2 to be squared plus, that's minus 3. Minus 3. Okay, I'm going to actually change that to plus a negative 3 so we can see it in this standard form that we have here. Okay, and so since I have that, I notice that my h is actually a negative 2. So when I see this positive and it's negative here, I know it's minus a negative 2. So x is equal to negative 2 is my axis. Okay. And then when I look at my vertex is the h value, which in this case is negative 2 from here. Okay. And our k is plus a negative 3, so it's negative 3, which is verified by the vertex that we found when we were doing our shifts. So we went over negative 2 and down negative 3, and so therefore that was our vertex, or from standard form, we can easily arrive at it by looking at h and k. We know it's going to be pointed upwards because a was equal to 1, and we know our axis of symmetry, okay, is this h value.